Hello kids, today we will be covering Unit 6 for Grade 8 Science, which is sound. So the first question that arises is what is sound, right? So when we define sound, that sound is a form of energy that moves from one point to another or transfers energy, right? So sound is a form of energy, right? That's the first thing. And it only happens when things vibrate, right? So we do know that when we hit a drum, right, the membrane of the drum, it vibrates when we struck it with the drumsticks, right? That creates sound. And in contrast to that, we also have guitar strings. When we pluck the guitar strings, right, the guitar strings vibrate, they move, and that's how we create sound. In lab, we also created sound using tuning fork. If you remember that this prong tuning fork, right, when we struck it, it started vibrating, and because of that, we heard sound, right? So what's the first condition that is necessary for creating sound is vibrating objects. So we can say sound is created by vibrating objects, right? So now if you feel your own throat while speaking, you can see that you can feel with your fingers that when you're speaking, your throat is vibrating, right? So eventually, vibrating objects are the only ones that can create sound. If something does not vibrate, the sound cannot be produced, right? That's the first rule. Secondly, now what is a wave, right? We do know that waves, uh, if you hold a string or a rope, and you move the rope up and down from one fixed end, right? One end is fixed, right? And if you move this end up and down, you create this this pattern which we call as a wave, right? These pattern. Now sound is also a type of wave, but it's quite different from these mechanical waves, right? Sound is also a mechanical wave, but it's a longitudinal wave. So we can say that waves are divided into two types. One is transverse, right? Like water waves, or waves of these rope, and the other ones are longitudinal, right? So longitudinal waves are those waves in which particles travel parallel to this. So sound is actually a longitudinal wave, and eventually we have only a few examples of longitudinal waves, right? We have several examples of transverse waves like water waves, right? I will say as water waves, right? So waves generated in the water, and then we have longitudinal waves which are sound. So what are longitudinal waves, right? I'll come back to these diagrams. So what's a longitudinal wave, right? Longitudinal waves are those in which the particles, right, particles uh, particles vibrate parallel to direction of wave, right? So wherever the wave is going, you can say that the particles will vibrate parallel to this, and this is easily understandable with this diagram. Let's have a look at this diagram, right? We see that when we create sound using a speaker, the speaker diaphragm, right? It's this front part, right, which moves forward and backward, right? What it does that it pushes air particles forward and backward, which in turn transfers the energy coming from this speaker, right? In this fashion. So whenever it moves forward, it creates a compression, right? Which is this part, right, where the particles are pushed together by this air diaphragm, right? And then when the speaker moves backward, that's when it creates a rarefaction, right? And rarefaction is when the particles are relaxed and they're farther away from one another, right? So in class we discussed that we can translate sound waves into these wave patterns, right? Waveform. So if we draw a waveform in contrast to this, we can say that the crust is the part where which is the upper or the more energetic part, right? The upper part is called the crust, but for sound wave we call this as compression, right? And the rarefaction, this lower part is called the rarefaction, right? And the difference between the distance between two crust or two troughs, right? Over here I will also mark another wavelength, right? From here to here, this is what we call as wavelength, right? We represent wavelength by this symbol lambda, right? So This is also a wavelength. Also, we can calculate the wavelength starting from one point for a complete wave like this. This is also 1 lambda. As you can see that this length, and this one, right? All three of them would be the same, right? This is what we call as wavelength, or the length of one wave, right? And then we have the term amplitude, which is the vertical displacement we see, or the height of the wave, right? This is what we call as the amplitude of a wave, right? So we'll further go into the details of this, but first we need to understand basics of how these transfer energy, right? So remember, in waves, whenever we talk about waves, they only transfer energy, right? So they only transfer energy, right? They do not transfer the medium, right? So for sound, it is very important since it's a mechanical wave, right? So they do require a medium, right? Requires a medium. And that's a very simple example that we can take, that if we have let's say a jar, right? In that jar, if I put a bell in there, right? A ringing bell, right? The bell is going to ring. So if I just pull out all the air, right? If I pull the air out of this jar, you will see that as the air is being pulled out of the jar, there are no particles, as these are air particles, right? So when there is no air left in the jar, you will not be able to hear any sound coming from this bell, right? The bell is ringing, right, because you're giving it electricity from outside. But if this positive negative, this electricity is still there, but you will not be able to hear any sound. Why? Because there are no more air particles like this, right? The air that was there. Since the air is no more there, hence no more sound will be heard, right? Now let's get into some properties of sound, right? The first property is the pitch, right? So what is pitch of the sound? It is how long each wave is supposed to be, how farther each wave is from another, right? Or how many number of waves are going in a certain length, right? So this is also represented as the frequency of the sound. We use the word frequency more compared to the word sound. But remember that frequency and pitch, they both represent how many number of waves go through in a certain amount of time, right? In 1 second. Let's say if this whole distance represents 1 second, right? Then how many waves are going in 1 second? As I told you that each wave is completed when it goes up and down like this. So this is one wave, there goes another, and this is going to be the third one, right? So there are 3 waves per second, right? So we call this as 3 hertz, right? Now, compared to this, if we have lower frequency sound, it is going to be a very long wave, right? And compared to that, if in 1 second one wave is going, we will call it as 1 hertz, right? So, what does the frequency represent? It represents how many waves are passing per second, right? So, waves passing per second, right? How many waves can pass in 1 second, right? That is what we call as frequency. This is also termed as pitch of the sound, right? So what does high pitch or low pitch means, right? When we have higher pitch, we say that the sound is shriller, right? Remember this word shrill, right? And if the frequency or the pitch of the sound is low, we call it a grave sound, right? Now, what could be the example of these two, right? Grave sound would be like a drum, right? Because it's very, you can say, a more graver sound, it's lower frequency. And compared to that, if we have a bell ringing, right, this would be a very high frequency sound, it is shriller sound. Another example would be men talking versus women, right? Women have a thinner sound or a shriller sound, while men have more thicker sound or grave sound, right? So that's low frequency. So men have usually by nature lower frequency sounds compared to females who have higher frequency sounds, right? Now the second term we're going to look into is the loudness of the sound, right? How loud the sound can be, right? Now loudness, I told you, is measured as the amplitude, right? We do know that the amplitude is represented by minus 2, like loudness is represented by this height, right? So the height, the greater the height of the wave, the more the loudness is going to be, right? And if this amplitude of the wave is low, the height is low, then it is going to be more quieter, right? Now over here, as you can see, the frequency is the same for both, right? They both have same frequency, but what is the difference over here? The difference is in the loudness, right? In the amplitude, right? So higher the amplitude, the louder the sound, right? And lower the amplitude, the quieter the sound, right? That's how we simply put a rule for this, right? So if we compare the loudness of two sounds, we can simply say if we hear a sound which is coming which appears to be very loud, we can say the amplitude is very high. And if a sound appears to be very quiet or less loud, we call it having a lower amplitude. Now remember, the amplitude also depends upon distance, right? So the amplitude depends on distance, right? That means, let's say if I'm standing closer to you and I start speaking at a certain loudness, right? It appears to be loud, but if I start walking away from you, you will hear that my voice or the loudness of my voice will appear to degrade or lower, right? So it depends on sound. So farther the source, right? Farther means quieter, right? And closer means louder, right? So if a sound source is closer to you, then it is supposed to be louder, and if you move away from a sound source, it would appear to become less loud, right? So that means amplitude varies inversely to the distance, right? The greater the distance, the less the amplitude, the less the distance, the greater the amplitude, right? So it also depends upon distance. On the contrary, the pitch does not change with distance. Remember, only the loudness changes with distance, right? So this depends on distance. This does not, right? The pitch does not change if you move away or closer to the sound, right? Now, then we have quality of sound, right? This is one topic which is not written in the book, but we have seen some questions in the workbook which refer to these, right? Even in the assessment we had questions referring to the quality of sound. So what is quality of the sound, right? Now if we talk about quality of the sound, we need to understand that different type of objects will create different type of waveforms, right? These waveforms will vary depending upon the type of instrument which is creating the sound, right? So if we talk about voice, as you can see, all of these have same amplitude, right? This one has a bit greater amplitude because the height is a little bit more. But if you compare this and this, all three of them have same amplitude, right? Same amp, right? Same amplitude. Sorry, I'm writing sample, right? Because usually I'm working with sound samples. So it's the same amplitude, same amp, right? But even if I take frequency into account, even if I take same frequency, you can see that this and this, they're different, right? Also, for the voice, you can see the lower part is different. So these sounds will appear to be different from one another. This is what we call as the quality of sound, right? Different instruments, if creating same sound, will have different feel, right? So this relates to the feel of sound, right? So how can you tell one instrument is different from the other? Let's say guitar versus violin, right? Uh, Both, if creating same frequency of the sound, you will definitely be able to identify both the sounds as different. Reason being, they both will have different feel depending upon the texture of these waveforms, right? We can say the pattern of waveform, right? So even if they have same frequency or same amplitude, they will still appear to be different. Reason being, they're coming from different objects, right? So different objects will create different qualities of sound, right? Now moving further into the sound, the next topic is wave interference, right? So what is interference of wave? Okay, here's an example, right? Let's say you're standing right next to a pond with a friend of yours, right? And you both throw a piece of stone in that pond at the same time. You will see that these circular patterns of waves will form, but a point will come when these waves will interact with one another, right? As you can see, this region that I'm marking, Over here, you see that the wave pattern is bit mixed up. This is what we call as interference, right? Interference means waves interaction, right? Where the waves interact, or you can say they come together. This is where we see interference, right? Now there are two types of interferences, right? When we talk about interference, we have constructive interference, right? Constructive interference is when you see that both the waveforms, right? As you can see, this is the upper part and this is also the upper part, right? So they will add up to give you a bigger waveform, right? This is what we call as constructive interference, right? When they aligned, right? When they're aligned, or they have what we say same phase, right? What is a phase? Uh, Same phase, right? Phase is same, right? Now this, remember, needs to have same frequency as well, right? Now, on contrary to constructive interference, we also have destructive interference. In destructive interference, as you can see, this is the upper part, but in contrast to this, we have a lower part, right? These will subtract, right? And eventually, if they have the same amplitude, they will create no sound. So as you can see, there is no pattern left, right? Oh, sorry, that's too big, right? Let me just change this because at times we do need different colors. So yeah, right? So over here, you can say that no sound will be heard, right? They will cancel off each other. Over here, you will hear that independent sounds were less loud, but this sound would be louder compared to the independent sounds, right? Now, there are other ways you can, discuss interference. I will create one more example, right? Which is partial interference, right? So let's say if you have one wave, which is this much, right? Like this. Let me draw. This is the amplitude of one wave, and you add another wave to it, which is probably slightly less loud, right? Oh, needs to be same frequency, right? Sorry, my bad. So right, so somewhat like this, right? So as you can see that the amplitude is somewhat less, so these will add up. As you can see, it's up versus up, and it's down versus down, right? So they will add up. So eventually the result is going to be a much louder sound, right? Remember, when the sounds are aligned together, they will add up, right? And another way, we can also have a destructive interference, but incomplete destructive interference. Let's say if there's one waveform, and I'm just going to draw one wavelet, right? So compared to this, if you have inverse sound, but not as strong as the other one, right? Oh, it became a little too loud, right? There we go. So let's say we have one sound that is not as loud as the other one, right? So only the amount, the amplitude, which is compared to this, will be subtracted, right? So as of result, you will see that the sound, if you add these together, the result is going to be a less loud sound, right? So you will see reduction in sound. Reason being, the amount that is there will be subtracted from there, right? So subtract the height and you will get the result, right? So compared to the original sound, which was louder, right, you will hear less loud sound, right? It's not going to be zero reason compared to this example, right? The example that we have over here. Reason being, over here they were equally heighted, right? Their height was same, the amplitude was same, so they cancel off each other, right? And compared to this example, where the amplitude is a bit different from one another, this much will be subtracted, right? So after subtraction, you're only going to get this much loudness, which is visible over here, right? Now this, obviously I'm using a drawing pad, so definitely it's a bit slippery, so I cannot make perfect drawings over here, but somewhat it's understandable that how interference works, right? Over here, as you can see, that this plus this added up to give you this louder sound. So this was one and this was the other that added up, right? Over here we had subtraction. right? So this was a bit about interference of the sound. Moving further, uh, we discussed the formation of the moon, right? So for formation of the moon, we discussed a basic, idea how how the moon was formed. There are several theories, but the one that is most acceptable is the one that considers uh, the collision of Theia planet, right? Theia planet collision theory, right? This is the collision theory that we work with, right? Also known as collision theory, right? Let me write it down. In collision theory, we say that MOVE was formed when a similar size, planet-sized object known by the name of Theia came around and hit planet Earth, right, in early times, and because of that hitting, we saw a collision between these two, and a ring of debris was formed, right? Just like you do know that Saturn has these moon rings, right? We call those as moon rings. Reason being because that's a debris, and eventually we're speculating that even Saturn is going to form two moons, right, from these moon rings, right? Why we call this as moon rings? Because this dust will collect together, forming a moonlet like this, right? So we say that our moon, the moon that is around the Earth, right, was formed by this collision theory, right, in which a Mars-sized planet by the name of Theia collided with Earth, and it took some of the debris. Now, what are the factors that support collision theory, right? How do we know that this theory is acceptable? Factor number one is that same rocks on moon as Earth, right? Both Earth and Moon have similar rocks that are found, right? The structure of the stones on Moon and Earth appear to be the same. I gave you the name. We call it regolith, right? Regolith is the rock which is common both on Moon as well as on Earth, right? Many mountains on Earth are also of the regolith material. We say that when these two collided with one another, they exchanged material. Obviously, some of the material from this Theia planet was left on Moon, which we have the regolith mountains, right? Some of the mountains on Earth, as well as the whole structure of the Moon is also regolith. Secondly, why we say that it must have been a planet? Reason being because when we look at the structure of the moon, it has a functional core, right? There's a core inside moon which is functional, right? So usually moons don't have cores, right? Only planets are supposed to have cores. That also supports the theory of another planet hitting Earth, forming this moon, right? If there were no core, we would have gone for other theories. I'll go about other theories in a moment, but remember this: the importance of this presence of the core is very important, right? Moons do not have cores, right? Our moon surprisingly has a core which also generates magnetic field, right? So there's bit of the magnetic field around the earth, right? Sorry, around the moon, magnetic field of moon, which is very weak compared to earth, but it does have a magnetic field representing that it must have a core. We haven't seen the core either of the earth nor of the moon, but just by the presence of magnetic field we can tell that there's supposed to be a core inside it, right? Usually, let's say if we talk about the moons of Mars, we say that they do not have magnetic fields that represent that they don't have a working core, a moving core, right? Compared to that, our moon has a moving core, right? Now, further, collision theory can further be supported by two factors. Number one, I told you about the rocks, and number two, sorry, is presence of core, right? So these two factors, presence of core, right? These two factors are the major factors that correlate to the collision theory, that the collision theory may be considered as accurate. Although, on contrary to this, there are other ways in which moon can be formed, right? Now, I've listed this document, right? A little bit of read. You can pause this video to read this, right? So I will narrate this nonetheless, that there are four ways in which the moon could have been formed. There are four theories in which there is the giant impact model that we usually discuss, right? This is the collision theory, right? In this classical theory, we say that the Theia planet collided with Earth, right, it formed a dust ring around the Earth, and eventually those debris joined together, because in space things join up together because there's a lot of gravity, and because of gravity this moon was formed, right? Now this is the collision theory that we discuss. Then we have the synestia theory, in which we say that in early times when Theia collided with Earth, both of them were destroyed completely, right? And as a result, we had a rotating synestia, which eventually formed after cooling one Earth. Right, Earth was also formed because of it, as well as the moon was formed. Right, remember in the collision theory, we only say about the formation of the moon, and we say that the Earth retained its own presence. Right, but in synestia theory, we say that both Earth and Moon were formed after the collision, right? As you can see, the whole thing collided and bursted, and that is a possibility, because if something as big as Mars is going to hit Earth, definitely Earth is going to be in pieces, right? It's not going to survive this much of a collision, right? This big of a collision. Then we have the moonlet theory, right? The moonlet theory suggests that small projectiles, just like Theia planet, unlike a bigger planet, right? As I said, if something big as a planet would have hit Earth, then synestia theory would be acceptable, right? Uh, but in moonlet theory, we say that small projects kept coming, and they hit Earth and eventually forming small moon rings. And when they keep coming, right, different asteroids, they kept coming, they eventually joined together, forming these small moonlets. And when these small moonlets join together, they form the bigger moon, right? In this case, Earth can survive while moons can be formed, right? Then we have the twin collision theory, right? In the twin collision theory, right, this is just like the collision theory, right? We have the simplest theory. This possibly has formation of the planetary system, right? That if something like this did come, right, if this Theia planet had come, then where did this Theia planet was formed, right? So there's another problem, that if Theia planet was there, why was it not orbiting the sun, and instead it collided with Earth, right? So there are many issues. We can say there are factors that support the collision theory, and there are also information, or we can say speculations, right? Observations that do not support the collision theory. Now, both those are listed in your book. I would recommend to go through the context of the book over here, instead of just what I'm suggesting, right? Please go through the book over here, because book has described these phenomenon very, very accurately and in very much detail. So I would rather suggest to go through book instead of going through the internet or any other information, right? Because while solving the assessment or the workbook, you will have to restrict yourself to the context that is available in the book, right? So please, I will write it over here just in case, right? Read book, right? For this case, please go through the book for this context, right? Now moving on, we discussed nebula, right? So what is nebula? In space, when we look out at night sky, and we take up a very big telescope, and when we look out, we see these cloud-like structures in space, which are extremely big, right? Extremely big. We call these as nebula. So what is a nebula, right? So nebula can be described as an expansive cloud of gas and dust found in space, right? Now it resembles a celestial nursery. Why? Because you will see that stars are being formed inside these giant glass clouds. Now this very specific picture that I've taken from you, for you people, this is what we call as pillars of creativity, right? And why we call this as pillars of creativity? Number one, that this is nearly at the center of galaxy, not galaxy, I'm saying center of universe, right? We are a bit off the center of universe, since we are moving away from the center, right? So this is in the center of the universe, and we can say this is the biggest star factory we have observed, right? Biggest star factory, right? We call this as star nurseries or star factories, right? There's both works, but I would rather want you to retain to the star nursery or celestial nursery terminology used in the book, right? Now These formations exhibit diverse shapes, sizes, and hues. Hues mean colors, right? So they are if different colors, different gases representing different colors, right? And sometimes they have their own light, right, because they are creating stars, so definitely they glow very bright, right? And sometimes they are dark when they're not forming stars. Maybe the stars are blown out, or they got destroyed due to collisions or something, and eventually they reflect light from neighboring stars. As you can see, this appears to be a bit darker because of the background, which is very bright. Other stars at the back are giving light, so this star factory is creating several stars like sun, right? So this is what we call as nebula. Now there are several types of nebula. This I've taken directly from NASA website, right? The book is listing some types, but I've taken these five major types that the NASA is representing. Why I'm taking NASA's content? Because we do know that for space studies, NASA is the pinnacle of space or astronomical studies, right? So whatever the book is containing is just a fragment of the information what NASA can provide. I would highly encourage you people to go through NASA website. You can see the space programs and all the intricate information which is available about stars and these nebula, right? So there are several types of nebula. Number one is the emission nebula, right? As I said, emission nebula are those which have their own light, right? They emit, emit. I've got a T over there. Emit their own light, right? That means uh, they are generating stars, right? Definitely, if they are generating their own light, that means they're generating stars or they're producing new stars, right? Let me call it new stars, right? And then we have dark nebula, in which we do see these black clouds, right, which are not glowing, appear to be like shadows in the night sky, right? Big, large clouds, and they do not have any new stars. No new stars, right? They are not forming new stars because probably they formed stars and the stars would have exploded or something. They collided with one another, maybe unstable, right? Unstable stars. So that's why they appear to be dark, because no more stars are being formed and they are obscuring the light from coming from stars at the back, right? As you can see, the stars at the back, sorry, right, stars at the back are making it visible, otherwise you won't be able to see this dark cloud. Then we have planetary nebula, right? These are large bright nebula which have planetary systems, right, solar systems, one like ours, right? uh, our galaxy was also formed by somewhat like a planetary nebula would have formed a galaxy of ours, right? Then we have a reflection nebula. They don't have the stars of their own, but they are glowing because of the nearby stars which emit immense light, and because of that they glow and appear to be reflective, right? And finally we have the supernova remnants, right? These are large scale nebula which appear to be like in spherical shapes. They represent explosions, right? When stars explode, they create circular waveforms of glowing light. In the middle it's dark, right? Center is dark, and we have bright rings, right? That represent that something exploded in the middle. At least a very large scale star, very large compared to our sun, has exploded. This shows a supernova remnant or supernova remnant nebula, right? So different names are used in the book, but I would again advise you to use terms or names from book, right? Again, I will refer you to book reading over here, because again, when we talk about examination, we have to stick to the level at which you people are studying. Again, this I've taken from NASA to just give you a more detailed or more accurate imagery compared to what the book has to offer. Book is offering very limited information regarding these topics, as for me these are the most fascinating topics in science, right? I myself am a student of astrophysics, although it's not my subject, but I just study this for the sake of fun, or you can say as a sake of hobby, right? Finally, we studied plate tectonics, right? So what are tectonic plates? Now, since we're talking about formation of large scale objects, so Earth is also, this is Earth, and this is, you can say, an exploded view, right? Exploded view means that over here you can see that inside is the mantle, right? And these are tectonic plates, right? And we can say that, as you can see, some of the continents are broken over here, right? They appear to be part of two tectonic plates. And if you look at these appear to be jigsaw puzzles, right? So we've used the word jigsaw puzzles, right? And that is why we say that these tectonic plates would have been one single, right? One single large plate, right? One single large plate, right? That definitely broke down, maybe because of the dinosaur killing asteroid, right? It broke it down into several plates, right? And then these plates are moving because the mantle is hot, and that's a liquid which moves around, and that makes these plates move. So this is another view that some of these plates which are there, as you can see, they fit together like a jigsaw puzzle, right? And hence we say that these plates would have been one single piece which got cracked when something large hit Earth, right? Probably, maybe Theia planet, right? Or maybe asteroid, dinosaur killing asteroid, or maybe something afterwards, or maybe before. So again, these are just theories. We can just only look at the present evidence in which we see these as tectonic plates fit together as jigsaw puzzle, right? Now these tectonic plates move, right? So the tectonic plates move, right? And how do they move? This is due to the convection current coming from this core. Now, if you remember in the workbook as well as in the assessment, there was this question in which you have oil, right? And you had two biscuits, right, floating on top, or two plastic plates, right? And you were heating this from the bottom, right? So once you heat it up, so this over here, they were simply asking that what does the candle represent? It represents the core, which is the hot core, right? The hot heat coming in. And what was the liquid? The liquid represented the mantle, right, which can flow. The mantle is partially flowing liquid. It's denser liquid, right? Molten rocks, right? We do know what Malton is made of. Mantle are liquid molten rocks. And then on the top we have the crust, right? And the bottom layer of the crust is the tectonic plate, right? So when these hot air, now if you do remember in the thermal we discussed, then whenever you heat something up, right? When you heat up liquids, so particles, they become less dense and they move up, right? And when they move up, definitely they have to create a cycle, what we call as convective cycle, and eventually this cycle works, we call as the convection cycle, right? When we heat liquids, right, compared to solids. So due to this, these plates will move right, away from each other, or maybe collide with one another. If you consistently keep this moving, right, they will keep on moving around and they will hit each other as well, right? So these plastic plates represent tectonic plates, right? So this was what was given in the workbook as well as in the assessment, right? So you can go through the detailed version of this diagram. As I said, your book is not giving much of the information regarding these topics. I don't know why, but still I collected these images specifically for you people to go through complete information, right? I will just go into a simulation as well that I used to depict some of these experiments. I love to simulate these things on my computer. So when you see that these hot convection currents move up, they create these oceanic ridges, right? They create these mountains in which the tectonic plates are going to move away from one another, and when they collide with other tectonic plates, they also create these sunken zones or subduction zones, right? So there's a more cross-sectional image, which you can see that if you can see one plate is moving this way, the other one is moving this way, it is going to create an oceanic ridge. This is going to create mountains on one side, and on the other side the ridge is going to go downward, right, creating this oceanic bed, right? As you can see, these, how do we get to see these? Because on the ocean we see these ridges, right? Ridges or cliffs underwater, which represent these tectonic plates, right? The presence of the tectonic plates. So some of the evidence in the question, we have evidence for tectonic plates, right? Evidence number one is ridges, right? Ridges and mountains, right? How they are forming, how they are there. These represent tectonic plates, right? The tectonic activity is there. Secondly, earthquakes, right? Uh, there is no other possibility for the earthquakes to be there if these tectonic plates did not move, right? And these are the two evidences that we use. Number three, we say that the fossils, right? Obviously, over here in the first image, as I said, that one part, let's say if one part of the dinosaur was here and the other part of the dinosaur was found on another piece of the continent, we can say that probably these two ends, which are no more together, would have been together at some point, right? So the fossils also give us this idea. Then we also studied the magnetic, uh, number four, magnetic rocks, right? Since magnetic rocks, they appear to only change direction when there is a change of movement in the tectonic plates, right? So these magnetic rocks are also there. So we usually use the fossils and the magnetic rocks as evidence, but we also have the evidence of earthquakes as well as the ridges and the mountains that represent that tectonic plates move and they would have been together once, right? Now again, this is additional information, right? Additional info for you people, that what type of interactions are there between the tectonic plates, right? So there are three types of collisions, which are divergent, convergent, and transform, right? These are the least destructive ones, right? Because these, when rub on linear sides, they do not create much of a difference. Then we have trench formations, and then we have ridge formations, or we can say mountains formation, right? So these are, you can go through this context which is there, right? The motion which is spreading, like the plates are moving away from one another, you see cliffs forming, right? Then we have subduction, in which mountains or ridges are formed, trenches are formed, right? As a result, volcanoes are also forming on the side which is going up, and the side which is going down creates a trench or this ridge, right? And then we have the lateral sliding, in which there is no much of an issue, right? It is conservative, so there is no change on the terrain, right? But you see minute earthquakes coming around, right? So this is what I'm using as a simulator. This is a snapshot of the Labster virtual lab, right? I'm using, this is Labster virtual lab, right? It's a software that I use for simulating. I was just simulating this convection current and how these things are working. This is this is my robot, which talks a lot. And I was just progressing through what is going to happen if we see these convections, liquid magma going up, and liquid magma then moves around these tectonics and then comes back around after cooling up. So as I said, I use different softwares, right? This is another view that I was doing with honey, water, and lava. The same experiment we were studying in the book. So I wanted to do this, in the software in the Labster. So I selected these materials and I built this tiny little experiment, and I was doing this. So I was observing that how this is progressing. You can see that the convection currents are also there, again forming there. So the plates were moving about, right? Unfortunately, I couldn't store the imagery for this, because on OneNote I can only put pictures, and it's not possible to put videos over here. I would definitely put some of these simulations on YouTube if I got some time. But for now, for the sake of just your review, please go through the book, because for this Unit 6, I would highly recommend for Unit 6, use book, right? Please go through the context of the book, read the context. don't go through the activities though, right? Because I've covered the activities in this video, right? This was the only considerable activity which I found in the book was sensible enough, right? So rest, just go through the context, remember the terms and technologies. You don't need to memorize things because we just need to understand basic concepts. Please remember that these evidences are very important. So please go through the context and cover each and every page by reading through the context, right? Now that's it for unit 6. Definitely, if you have got any questions, please post in the comments or just text me on WhatsApp. I'll definitely try to respond as soon as possible, right? Thank you so much.